So welcome everyone to the second webinar. And today we will uh, see how to just some basic concepts of what it means to train a model, the kind of um, algorithm that we use for this, and then how you can use the platform to um, train your own model. So model training, what is it? It's just like you teach a child how to recognize patterns or make decisions by showing them examples. So in this case, let's say this child that you're trying to teach is the model, and the examples are the data, like pictures or texts or numbers. In this case, we are specifically dealing with images. And the goal is to help the AI learn from these examples so it can make predictions or decision on its own when it sees something new. So the main steps, you essentially start with data. So let's say you want to teach AI to recognize cats in pictures. What you have to do is gather thousands of pictures, some with cats and some without, label them, and that would become your training data. In our case, for example, our base model 2 is where we try to just say, this is blood vessel, this is not. Then you build the AI model. So the model is blank, it doesn't have any knowledge yet. And but as you show it data, it has the potential to learn. So this is the learning process. And this is made up of mathematical rules and algorithms. So it's mostly math um, and computer graphics related uh, approaches. Now you show the data to the model, you feed the labeled pictures into the AI model. The model looks at this picture and then tries to guess whether it's a cat or not. Once it has done that, it will look for mistakes, and it will see how much of it was correct, how much was wrong, and then it will go to the next iteration. Wherever it is wrong, it will try to see what are the features that's making this right or wrong. So it will learn. So this will be the learning process. And when we say train a model, this is what we are mostly referring to. And then it's repeat and improve. So you keep going through this process till you reach certain level of accuracy. Um, so you repeat this process many times, showing the model more and more examples. Each time the model gets a little better at recognizing cats. Now, the next step would be testing the model. So once the model has been trained, you test it on new pictures it has never seen before. If it performs well, it is ready to be used in the real world. So this is when we were recommending that you upload your own images and test out the base model on your images and see how well it does. Um, so key concepts, when we talk about model, it's the brain that learns from data. Training data is the examples you use to teach the model. Learning is the process of adjusting the model's rules to improve its performance. And testing is checking if the model can handle new unseen data. Now, when it comes to image analysis, there are, of course, many different algorithms, but one of the very commonly used one is convolution neural network. It is a type of artificial intelligence model that's really good at understanding images and patterns. It's like giving a computer a pair of smart glasses that help it see and recognize things in pictures. So how does this actually work? So imagine you are looking at a picture of a cat. A CNN does not see the whole cat at once. It looks at small parts of the pictures, like the ears, eyes, or whiskers, and then puts all of those pieces together to figure out that it's a cat. In a little bit more detail, uh, you first break the image into small pieces. The CNN uses something called a filter or a kernel to scan the image. And there are different types of filters that are used. And what it can give you is something like the edges, the corners, colors, all of that information. So when you consider one pixel or one dot, it also looks at things around it and calculates some of these features. So it then detects simple patterns. So in the first layer, the CNN detects simple patterns like lines, curves, or dots. Then in the next layer, it'll go through multiple layers. Next layer, it will combine patterns into complex features. So as the image moves through more layers, it combines these patterns into complex features. So now combining curved edges to recognize a cat's ears or whiskers. In our case, let's say recognizing the lumen of the blood vessel. Then the whole, uh, recognizing the whole object, that would be the final layer, where it puts all of these pieces together and recognizes the whole object. So the key parts of it, and again, this is just for some understanding, but if you don't fully understand everything, it's fine. It's not really critical for you to know all of these to build your models. So there's a convolution layer. This is where the filters scan the image to find patterns. Then there is pooling layer. This layer simplifies the information by summarizing small regions of the image. For example, it might look at a 2 by 2 grid of pixels, so it'll be 4 pixels, and keep only the most important one. So this helps reduce the amount of data and makes the CNN faster. Fully connected layer is where the CNN makes its final decision. So it takes all the features gathered through all the layers and combines them and says, this is a cat. So this is in summary. It works by breaking the image into small pieces, detects simple patterns, combines them into complex features, and then recognizes the whole object. Now, specifically, of course, there are different CNN architectures. The one that we use is UNet. It's a convolution neural network designed for image segmentation, and it relies on hierarchical feature extraction to capture both low-level and high-level features from the input image. And these features are critical for accurately segmenting objects at the pixel level. So this is the name comes from the architecture being in the shape of a U. I will let Shashank explain this. So, Shashank, in the context of CNN, what is UNet specifically?
So, yeah, unit is for image to image segmentation. So you want to get a mask on the image. You want to classify every pixel into classes. Let's say in our case, whether it's a blood vessel or not. So in this picture, you can see, right, we are going from, let's say, input size or image, which is, let's say, 572 cross 572. And we are decreasing its size on the left hand side, you can see. And we are contracting it into a very small vector, which is, let's say, 1024 on the bottom side. And then we are again increasing it back to the image size, and we have arrows in between, like from left hand side to the right hand side. And while increasing its size again, where we are classifying the image, we are using the features that Dr. Namita just talked about. Like we calculate or get features at different levels, whether it's a lumen or not, whether it's a blood vessel or not. And we combine these information in between and finally create a mask, which is of the same size of the image. So that's where the name comes from. We first go down, like we create a bottleneck, which stores all the information about the image. And we then use that information to finally classify every pixel. Yeah.
Okay, so now how do we use the platform to do the training? So we covered how to do the annotations for this approach in the last webinar. Um, so you can have the view the recording of the webinar as well as definitely review the documents specifically for this purpose. Once you've done that, once you have your annotations ready, you will have to give the model name. So whatever name you wish to give, you can give that name, and then later on you can use that to run your inference, look at the model progress and all of that. You can of course rename it later if you want to. You have to choose model type. So in this case, you will choose the segmentation. There are two approaches, segmentation as well as detection. We don't use, or we are not recommending detection for this particular challenge. One of the reasons being that there is huge variation in the size of blood vessels, right? They can be very small, they can be very big, and that doesn't work as well with detection, at least in the current scenario that we have. So we highly recommend you use segmentation. Then the model architecture is UNet. And then you have to choose the training data layers. So if you've been making your annotations on, say, train data editable layer, you will choose that. If you've created a new layer and using that to make annotations, you can use that. You can also use multiple different layers. Let's say you are a team of four, and four people have made their own layers and they're doing annotations on each of those. You can combine all the layers for training. You will choose the different annotation types. If you don't choose anything, if you choose all, it will be totally fine. But if you have more annotations and you don't want to identify everything, you can subset it. And there is a filter existing button. If you click on that, then you'll be able to see how many total number of annotations for each category there are. So that's a useful tool to just check that. Now, other thing you will see is advanced settings. These are the 5 different things which I will explain in detail. So, or actually, I'll ask Shashank to explain this for now. Shashank, you want to talk about this?
Yeah. So epochs is something, let's say when you learn something, you always go through, let's say, a book multiple times, or you revise it multiple times. So same thing here, we go through the data multiple times. So you decide in like how many number of times you want to go through the training data and learn it. But yeah, let's say when you go through it, let's say infinite or a very large number of time, then this can happen. You uh rot learn it, like you just remember everything, but you do not learn anything. So you have to find a sweet spot there so that your model, what we call in technical terms, do not overfit, or it just not, or it should not just learn the data, it should understand the logic, what is the blood vessel. So that is epochs. Now batch sizes, how many questions you can do in a single attempt. So let's say there is uh, you can do in a single session 8 questions or 8 examples at a time. So batch size defines that. Train test split is you have created the data, you have annotated the data. Now you want to keep some of that for validation or testing, which is, let's say, you have a training data of 80% and test data of 20%. So now in your epochs, you will go through n number of epochs through your training data, and finally you will see how it is performing on your test data. So it's a data, uh, you are seeing ki how I am performing on the unseen data, and you want your model to perform not only good on training data but also on test data. So, but now again, there is a question, like it's a hyperparameter. You have to choose specifically. If you increase uh, the train test split to two, let's say 20 point or 90%, then your test data will be very low and you don't have enough example to judge how good it is doing on the unseen data. But if it's too low, then you have very less data to learn from. And magnification comes in this histopathology domain, because if you have a very high magnification, then you have a very minute details as well. Like you can capture very minute details, but then it again asks for very large amount of data. to learn on the high magnification, and it also takes a lot of time because your data increases many folds if you are training on high magnification. And patch size, again, going on to the same thing. If you are using, let's say, blood vessels uh, are very tricky, like they are very small also, they are very big also. And it also depends on the context as well. If you are using high patch size, you are capturing more context, but you are using more computation, and it is very heavy model then, and it takes a longer time to train with higher patch size. So yeah, these are the hyperparameters that we have to tune while training a model. You guys play with it, and yeah, first try and guess what is the best patch size you think and what is the best magnification you think is for uh, blood vessel detection. And yeah, start with that, I think.
Yeah, so I just want to give some examples of in this, the important part is the magnification patch size. So just wanted to show more examples of it. So this is the example where we are looking. So typically blood vessels, you would think they are best visible at 20x. Um, so that's the thing. Patch size is 1024. That is in pixels. Typically in micron, it will end up being closer to 2048 microns. And so this is the amount of, if you see the white line, the white square, this is what the machine will see. That will be the first input image going to the machine. Um, this is what we use for our base models. So where the magnification is 20x, but patch size is 512. So this again, the squares that you see, now it sees less information in a patch. Um, but it seems to have enough context to determine whether it's a blood vessel or not. So we thought this was a good option. Other one is even low, smaller patch size. So then in a given time, you will see only this square, but sorry, which would be fine for smaller blood vessels, but it can be less information for larger ones. Then this is at lower magnification, but it's the same size patch. Next is this. Then this, even at 5x, these are the options. So um, so as Shashank mentioned, uh, sorry, Shashank, do you want to just say?
Sure. So higher magnification, you are getting more finer details. You're capturing more final details. So you are finally getting finer contours, or you can say finer blood vessels. Higher patch size, again, larger context, more information you are giving, and it should be able to capture large blood vessels as well, but you should not increase this too much. Then your model is just overwhelmed with the information. It will not learn much. And increase size in inference microns, or let's say if higher magnification, higher patch size, your model will be slower. So slower inference, that again something you want to optimize for. So your model should be faster and should capture enough information, like with the minimum magnification patch size to get all the blood vessels. This is the goal for the challenge, I guess. Mm. These are the recommended values that we have tried, like different scenarios we have tried. We have tried different base models. And yeah, epochs 500 to 1000, it goes very quickly from, let's say, 10% to 80% very quickly in 150 epochs. But then uh, finer details it captures very slowly from that point to, let's say, 500 to 500 epochs, even 2000 epochs. It keeps improving. And batch size is something you should keep it fixed. Let's say till 512 batch size, keep the batch size at 32. And magnification 20x. You can always try with 10x and 40x. And train test split that we have mostly experimented with is zero point 0.8. It's quite a sweet spot. You have not very less training data, and also not very large or very small test data. So it's fine, or a very good sweet spot. Yeah. And these are the losses curves that we see. So losses, we talked about in the initial stage, right? You tweak the internal algorithms or rules. You have to make, uh, so every time your model sees the data, it predicts whether it's a blood vessel or not, a pixel wise, and it calculates how much error it is uh, doing on the images or on the prediction from while comparing it to ground truth. So your error should be as low as possible. As you can see, it is decreasing very quickly for early epochs, and then it is plateauing, but it's still decreasing. And you want your not just test loss to be very low, but your validation loss should also be very low. So in the first graph, we are seeing both the losses, but yeah, validation loss, I guess it's hidden behind the train loss. It's light green and dark green kind of. And then we have train loss per class also, which is whether it's a blood vessel or it's not a blood vessel. And then for the same, we have a validation loss per class as well, which shows for both the categories, whether it's a blood vessel or not, what is the loss the model is making. And again,
So
you can see, because not blood vessel is a very in very high quantity, like most of the pixels are not blood vessel. So model has very high, like it has a huge amount of data for that. So that loss is smaller than mostly for the blood vessel. So that's how it goes in machine learning. As much data you have, your model will learn. But again, uh, dump goes in, dump goes out. So quality of the data is also matters. So try and give the quality data, try and do the annotations with as much precision as you want, and it will surely help you build a better model.
yeah, I, I think that is one of the most critical part. And other thing I wanted to mention is like here you can see it is relatively smooth. Um, the curve is smooth going from first epoch to the thousandth epoch. And generally, if you have good data, like if your annotations are good, this is what you will typically see. I also wanted to show an example of a different training model that we had done, where you can see that the generally train data you will see consistent decrease because that's what the algorithm is trying to optimize for. So it will always get that going down. But if you see the validation data is all over the place, so the curve is going, it's very, very noisy. And then specifically for certain classes. So the first curve is all classes combined, and then the next two are specifically for each class. Um, and then you can see certain classes, the noise is just too high. Generally, if you see this, it most probably is due to the quality of the data. So when you start training and if you see something like this, then it would be a great idea to go and check your annotations. And these two curves can help you identify which annotations there might be an issue with. Next is just another thing is the confusion matrix. Shashank, go ahead with this.
So yeah, let's say we have a base model 2, which does whether it's a blood vessel or not. And in this, you see a confusion matrix, or you can see a comparison, like how well is my model doing finding blood vessels or not. So you can see in other, I'm able to find 99% of the blood vessels, but I'm calling, let's say 0.49% of them as BV, and same for blood vessel. We are able to find 95% of them, but we are calling 4.95% of them uh, as blood or other. We are not finding these blood vessels. So you will find it for every epoch. You can see the drop down and you will see the best epoch as well. This is automated, so you will get the best model itself stored. And yeah.
So this is again the same set of important resources. I wanted to pause for questions also at this point.
I'm Isha, I'm a pathologist, and
Yes,
I'm really happy you are trying to train some of us. I can recognize 2 other pathologists from St. John's, but I don't know how many are there. But taking so much effort to train us is something. And we are slowly learning, but we are running into problems. Dr.
right.
Julian is not here. She's the one who's been actively doing in my group. She said she was unable to add a layer. She's right now very busy with some other work, so she couldn't be here. So she told me to ask on her behalf. She couldn't add a layer. When she could upload some images, she's uploaded 2 images from our department, but she could not download them.
So yeah, we don't have the download options on our platform.
Okay.
So we only have the upload option. For layer, she should be able to create. So you can either send us a screenshot of what the issue is, or we can also always set up a call and um, troubleshoot what the problem
Oh,
is.
okay.
Yeah.
Do you have a common area where she can put in the questions and whichever of you sees that answers?
Yes, yes. So we do, Pranali, you want to talk about all the different options we have?
Yes. So, I think mostly she's been mailing us, right? I spoke to
Yes,
Dr.
yes,
Krasta. She has
yes,
mostly
yes.
been mailing us. Apart from that, one option is you can join our Slack workspace where you can post whatever questions you have, whatever queries you have, and
Okay,
one of us will get back to you.
okay,
Uh, I had sent the invitation link for joining the Slack workspace in one of my initial emails, but
okay.
I'm afraid it might be sort of
Lost.
deprecated. No, no, no. I think
Oh,
it suspends after a certain number of days, right?
oh, okay.
So I will regenerate one invitation link and send that to you. Other
Thanks.
option is what we have done is we've created individual WhatsApp groups for each team.
Okay.
If that is also something that you're interested in, you
Yes,
can get
that would
an
be very good.
yeah. So I will send my number on the chat here on Zoom. You can
Okay.
just ping me a message, hi, and get me the number of all the members in your team, and I can create a WhatsApp group with our tech lead, me, and Dr. Namita. And in case you have any issues, you can always just ping us on that WhatsApp group, and we'll get
That will
back
be
to you
great.
immediately.
That will be
Yeah.
great. Thank you.
So I've just left my number for anybody who needs to get in touch with me on the Zoom chat right now. So you can
Yeah,
just
thank you.
keep it. Okay. Thank you.
Yes, and I think one other announcement that I had was we are going to allow for annotations and training and all of that till end of March,
Thank you.
because I know it's one, it takes a lot of time, and then we couldn't do this webinar early enough. So just to give enough time to everybody. And yeah, so till end of March you can continue.
Thank you. Thank you so much.
Yeah.
Then one more thing Shashank mentioned, overfit.
Yes.
So, yes. So for the pathologists who are here, I mean, since I'm a pathologist and I understood what overfit meant. It is like when we look at a slide and we say, ah, yes, this must be a fungus. And then we start looking for the fungus, and after some time we start imagining some other structures are fungi. So
Okay.
I think that may be what you mean by overfit.
Yeah, it's
So
kind of an overfit, but let's say in I guess the curves that we have shown you, validation and training loss curves, in that you will see divergence in the validation loss. So you will start noticing like your training loss is coming down, but your validation loss is going higher, which
Okay.
suggests that you are just learning the data. Like you're not actually learning or deciphering anything what exactly the data means. So
yeah,
what happens, right? Like we can just remember all the questions in our exam, like that used to happen in our earlier classes, right? We just
Yes.
uh, learn or remember the questions and we don't understand anything. So that is what overfitting is now. There can be multiple scenarios for that.
Okay.
But
Okay.
very common thing is you should look at the training loss curves.
Okay. Okay.
So one of the main things overfitting happens in case of histopathology would be, let's say it will learn the wrong thing.
Hmm,
It
hmm, hmm.
will think, okay, color pink means this. So let's say your staining protocol is slightly different, and
Huh.
now your images, instead of pinkish hue, they are more bluish hue.
Yes.
Then it will not identify correctly because it has learned it all wrong. That
Okay.
it has relied its information on color rather than the structure, right? Ideally, for a blood vessel, you want it to look for a lumen, it need to look for an endothelial lining, those kinds of things. Instead of that, it may have focused too much on the color.
Okay.
So that's what happens in case of overfitting, and that's why you will see in our case also the base models also it has overfitted, because when you will run it on your own image, you will see all the mistakes it makes. And typically, what we see is once you do it for 3 to 4 to 5 different institutions or different types of images, it works much better.
Hmm,
And
hmm.
we do use augmentation techniques and all to account for it, but for some reason, the real data actually always works much better than synthetically created variations.
Yeah. Okay. Thank you.
Great. Any other questions? Okay, great. So thank you so much, everyone, and happy training. We really look forward to some amazing models coming out of this.
Hello, ma'am.
Yes, yes.
Myself Chandrakala from St. John's Research Institute. I'm from Dr. Jyoti's group. So I have a question.
Yes.
Could you please show us how to import the images?
Yes. Let's see. Okay. So once you go to the data set from the platform page, there is an add image option here.
Okay.
Once you choose add image, then you can use the file. Let's say in this case, I should choose something small. So let's say I chose a file, and typically it will automatically calculate magnification. But in case it's not able to figure out, for example, PNG files don't actually have that. In that case, you will have to give the information yourself. And if you don't know the exact MPP, just choose the magnification. That is also fine. So you can, if you know if the image was taken at 20x or 40x, then you can choose that. Rest of it is not critical to enter, so you can skip that and then you just say confirm, and then it will get uploaded and it will show up here. So I don't know if yeah, okay, yeah, so some random image, but yeah, it'll show up like this. And then, because I think I can, okay, I can't delete it right now. Yeah. So were you facing problems uploading an image, or this was not very, or you just didn't know this was the place to, from where to do it?
Yeah, yes, ma'am. There was some confusion. So, yeah, thank you so much.
Okay. And again, the documentation page, we have updated it. There was a little bit of some information was not updated because we keep making improvements, but now it's updated. Also, there you will also find we've also added the Amaranth challenges column. So there you can see all the previous webinar and all the other information is also here. So you can quickly get to some of these things, right? You don't have to, it's been time stamped and also you don't have to go through the whole webinar, but just some specific information if you've missed, you can check that. And again, this documentation page is accessible from here. So there will be a documentation. If you click on that, you'll come to this page.
Sure, ma'am. We got it. Thank you so much. That was helpful.
Great. Thank you, everyone. Have a nice day. Bye.
Thank you. You too.
Bye.